Coming up on Dr. Kiki's Science Hour, we're talking about the holographic principle with Dr. Raphael Bousso from UC Berkeley. That's up next on Dr. Kiki's Science Hour.
Netcasts you love.
From people you trust.
This is Twit. Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour with me, Dr. Kiki, episode 109, recorded on Thursday, August 18th, 2011. Are we Princess Leia? This episode of Dr. Kiki's Science Hour is brought to you by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly. All streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Welcome, everyone, to Dr. Kiki's Science Hour. I'm Dr. Kiki, and this is episode 109. We're getting up there, past 100. I love every week a new and a different show. And this week is going to be no different. We've got something new, different, interesting, exciting. So I hope you're ready to dig into our 1 hour, one topic, one expert. And this week we're going to be digging in to the topic of the science of the holographic principle with physicist Dr. Raphael Bousso. He's from UC Berkeley. But before we get into our big conversation of the hour, some science headlines. UC San Diego scientists have discovered a new player in our genetic material. Halfway between DNA and a nucleosome, the pre-nucleosome will open doors to understanding how DNA is packed with histones to form chromatin. If nothing else, the discovery will force a rewrite of a chapter or two in some textbooks. Scientists using data from NASA's Stereo Solar Observatory spacecraft have published detailed images of the solar wind, identifying structures within it like the solar wind piling up at the leading edge of a coronal mass ejection, voids in the interior, long thread-like structures, and rear cusps, magnetic disconnection phenomena called plasmodia, puffs that correlate with in situ density fluctuations, and V-shaped structures. What's all this imaging good for? Well, it will allow scientists better understanding of the large-scale structures that affect the solar wind and impact spacecraft and our planet. A study by Lars Borg at the Lawrence Livermore National Lab of Moon Rocks, brought back to Earth by the Apollo 16 mission, puts the age of the moon at 60 million years younger than the other estimates. This is either wrong, or scientists need to rethink how or when the moon formed, which might work well with the news of the big splat that we heard about last week. You all know the movie Deep Impact, where the giant asteroid is on a collision course with Earth and Morgan Freeman is the president, and the U.S. tries to deflect the asteroid, but it still ends up splashing down in the Atlantic Ocean? Yeah, well, scientists want to try that with the asteroid Apophis that is supposed to maybe hit us in 2036. Just change the United States to China and change the mission craft's prototype nuclear propulsion system to a solar sail. Paleontologists and physicists teamed up to figure out when the brains and sensory organs of jawed vertebrates were reorganized in the evolutionary jump from jawlessness to jaws. They used a synchrotron particle accelerator to produce X-rays that allowed non-destructive 3D microscopy of the brain cavity of a 400 million-year-old Galeaspid fossil, which is an intermediate evolutionary step between jawless and jawed vertebrates. Then they found that, yes, indeed, the brain was reorganized before jaws hit the evolutionary scene. Researchers have linked sex disruption in wild gudgeon, which is a type of fish, in a river in France to a Sanofi pharmaceutical company plant. Dexamethasone, an anti-inflammatory and immunosuppressant, spironolactone, a diuretic that blocks male sex hormone effects, and canrenone, a diuretic, were measured at around 10 micrograms per liter. On average, at least 60% of fish from the river near the plant had both male and female sex characteristics. Compare that to 5% further away from the plant. The company says it is cooperating with regulatory agencies as the investigation continues. Scientists in Singapore have used synthetic biology to equip a strain of E. coli with the tools to kill another bacterial species. Pseudomonas aeruginosa causes lethal infections in humans, but succumbs to a protein called pyosin S5. The E. coli was given the gene for pyosin S5 and the instructions to burst open and release the toxic protein when it encountered the chemicals that Pseudomonas bacteria use to communicate with each other. In lab tests, less than 1% of the Pseudomonas bacteria survived the attacks. A team of researchers has identified a strain of bacterium, Serratia marcescens, as the pathogen that is causing a disease called whitepox in Caribbean elkhorn coral. The pathogen is found in human sewage and is the main reason that the elkhorn coral in the Caribbean have been listed as a protected species. Hide your kids, hide your wife. Hyenas can now count to 3, or we've found out that they can count to 3. Hyenas can count? Just like monkeys? What? Well, zoologists found that wild spotted hyenas were able to distinguish between the calls of 1, 2, or 3 unknown intruders to their territories, making hyenas seriously one of the scariest animals that I know of on the planet. And now, something that I love to count on, my weekly sponsor message from Netflix. This episode of Dr. Kiki's Science Hour is brought to you by Netflix. Netflix streams thousands of TV episodes and movies directly to you instantly, which means that you save time, money, and hassle. There are several easy ways that you can instantly access streaming movies and TV shows with Netflix. You can watch Netflix movies and TV shows on your Mac, PC, or iPad, even on your iPhone or Android phones. If you have a gaming console like an Xbox 360, PS3, Nintendo Wii, you can watch Netflix right on your TV using one of those. Or if you're not a gamer, but you have one of those set-top boxes like a Roku box or even an Apple TV, you can use that as well. Inexpensive, easy to use. With Netflix, you can watch movies and TV shows instantly using any of these devices. You can begin on one device, stop watching, switch to another device, and continue watching to the end of your show. So you're not stuck to one location to be able to finish your program. Whichever way you choose to access Netflix, you can watch as many movies and TV shows as you want, anytime you want, and you can cancel at any time. So try Netflix today, free for 30 days. Go to netflix.com/twit and use this URL when you sign up for your free trial. It's a free trial, Netflix, netflix.com/twit. We thank Netflix for their support of Twit and Dr. Kiki's Science Hour, and we hope that you enjoy watching instantly with Netflix. Back to the show. It's time to bring in our guest expert. Raphael Bousso received his PhD from Cambridge University in 1988 and went on to become a postdoc at Stanford University. He worked at the Kavli Institute for Theoretical Physics in Santa Barbara, and he has been a fellow at the Harvard University Physics Department and the Radcliffe Institute for Advanced Study. In 2003, he joined the Physics Department at UC Berkeley, and his lecture, The World as a Hologram, is featured in Lawrence Berkeley National Lab's Summer Lecture Series, and you can catch that online. But we have Dr. Bousso here to join us and talk about the holographic principle today. Dr. Bousso, thank you very much for joining me today.
Thanks for having me.
You're welcome. So, as a physicist, a theoretical physicist, can you tell me what gets you excited or got you interested about thinking theoretically? And spending your time thinking about the way that the world works?
Well, it's not really the theoretical part that got me excited. What got me excited is the idea that we can understand how the universe works by asking about regularities, by discovering that there are laws we get deeper at how nature is actually put together. We learn things like the fact that what makes an apple fall to the ground from the tree is the same force that keeps the moon going around the Earth and the sun and the Earth going around the sun. The idea of unification, that lots of phenomena which look like they're completely different are actually manifestations of the same underlying laws. That to me is very beautiful, and so the theoretical part has to do with somebody's going to go and guess what these laws are, but if you don't start by looking at nature, if you don't start by making observations and by doing experiments to understand what's actually going on, then there wouldn't be any theoretical things to be doing, right? The theoretical part is sort of trying to take all these phenomena that are out there and see patterns in them and understand what can explain them from some very simple ingredients, trying to explain all those different phenomena.
Do you think simplicity really is the key? I mean, I've heard other physicists say that the shorter the equation, the better the equation. Is that a truism?
That's perhaps a little oversimplified in one sense, but it's true that clearly I could give you a description of all phenomena that we see by simply writing them all down on a piece of paper. Today I saw an apple fall. The day before I saw the moon going this way or that way. I could make an incredibly long list that at all times has everything on it that we've ever observed. And I could say, well, this is a great, summary of everything we know. What more do you want? Mm-hmm. And it should be intuitively clear that this is not very satisfying. For one thing, because it's so complicated and long and inefficient. But a sharp way of saying why it's not satisfying is that it doesn't predict what's going to happen next. It doesn't allow you to figure out what the moon is going to do tomorrow. It doesn't allow you to figure out what happens when an apple falls from a different tree. And so there is a relation between simplicity and how much you're able to predict about what's going to happen. The simpler your theory, the more you've got left to predict. The more complicated theory, in a more complicated theory, you're already putting in a lot of stuff by hand. And if it's decent theory, it'll still make some predictions. But it's nicer to have a theory which is even simpler. There are even fewer ingredients that you get to dial or play with. And more comes out.
Where does the holographic principle fit into the landscape of the theories and models that are available in physics that people are working on currently?
Well, it fits very nicely into this story of unification. The holographic principle, we believe, is an important hint that nature is giving us about how to accomplish the last very major piece of unification that we are still trying to do. So just to give you a little bit of context, the early 20th century saw the development of two major pillars of science, physics in particular, one being quantum mechanics. So that's usually thought of as the science of the very small, how atoms work. Inside the atoms, there are nuclei, how those put together, what are the forces that act between them. The theories that tell us how these things work, to unbelievable precision, by the way, are all based on the notion of quantum mechanics. And this has been a huge success story, and in particular, we have a theory called the Standard Model, which really explains the different forces that interact in atoms, and including forces that we can see in the macroscopic world, like electromagnetism, radio waves, how these are all really unified. They're all coming out of a single theory that we've, I think, pretty much nailed down completely. But there's also this other part of physics, the science of the very large, the universe, maybe not that large, the solar system, galaxies. For all those things, you need to understand gravity. Gravity is a force which is, in some sense, weaker than the other forces that we know, but it piles up. And so if you look at very, there's no positive and negative charges that can cancel in gravity. Everything's attractive. And so if you look at larger and larger scales, gravity is more and more the dominant force. And so also in the early 20th century, a beautiful theory of gravitation was developed called general relativity by Albert Einstein. And that's still the cutting edge, almost 100 years later.
Yeah.
And it's a beautiful theory. It explains in great detail a lot of things about what we see going on in the solar system and on larger scales. But it is not compatible with quantum mechanics, at least on the face of it. It's certainly not a quantum mechanical theory, and there are a number of reasons why it is very difficult to make gravity fit in with the whole quantum mechanics scheme. So for other forces like electromagnetism, so on, we developed after a while a sort of recipe that we could follow to kind of take the classical theory that we already had and then quantize it. And that's the actual word. And with gravity, that just blows up in your face. Gravity is somehow different. It's somehow a completely different character in this game. Naively, it seems like, hey, this is just another force. Let's quantize it. But the reality of it is that it's a much harder nut to crack. And the holographic principle is one of the reasons why, and at the same time, it's something that it's one of the reasons why it's hard. But it's also an amazing observation about the relation between information content of the universe and its geometry, a relation that may actually be hinting at how we should be constructing a theory of quantum gravity, a theory which brings these two pillars of 20th century science together and really gives us a completely unified description of nature.
You mentioned earlier that there's no positive and negative particles or forces for gravity. I don't know if you're aware of this particular study. There's one that's just come out, and I think it might be on Archive. So it's a preprint by a CERN physicist, Dragan Slavkov Hadjukovic, I believe is his last name, and he has written a paper about dark matter and saying that it might be an illusion, and he proposes a virtual gravitational dipoles, so that there is a positive and negative, there are positive and negative gravitational charges, and he explains this way of that they would work to create the illusion of dark matter. Maybe
you should invite him to your show.
I know. It'd be an interest. It's just another interesting idea. It's like every time somebody says there's this or not that, there's another physicist out there who's got an idea about stuff. In terms of the holographic principle,
not all physicists are equal.
No, it's true. That is very true. In terms of the holographic principle, bringing these things, the quantum universe and the large macro universe together, can you explain a little bit about how the principle works and how we might be existing in a hologram?
How it works is precisely the question to which I have no good answer at all.
Okay.
But I can tell you what it is.
Okay.
It's a statement about, well, as I said, it's a relation between information content of space-time regions and the geometry of space-time. So first, I should perhaps just give you an ordinary everyday life feel of what I mean when I say information. Okay, so we use the concept of information all the time. When you buy yourself a bigger hard drive, what you're really saying is, there's too much information that I want to store, and it doesn't fit on the hard drive I currently have, so I have to buy a bigger one which can fit more information. So just think of it as the amount of bytes or megabytes or whatever that you might want to store on a hard drive. I mean, 100 years ago I would have said, think of it as the number of letters that you can fit on a piece of paper. Okay. Now, with both of those technologies, writing and hard drives, there's some flexibility as to how densely you store your information. With computers, of course, we're able to store more and more information in less and less space. It's very impressive. But also, when you write on a piece of paper, you could ask yourself, well, how many letters can I actually fit on this piece of paper? And obviously, it depends on how small you write the letters.
Right.
And this is, now we're starting to get a little bit in the direction of what the holographic principle talks about. The holographic principle is a statement about a sharp upper limit on the amount of information you can store on a piece of paper, or more generally in a region of space, no matter how small you write, no matter how far you develop hard drive technology or whatever follows after that. And there's a fundamental limitation to how much information you can store in a specified region of space. Right. That in itself is perhaps a little bit surprising, because again, you would think that you could just go use smaller and smaller scales, use smaller and smaller particles, or just try to cram things, try to use very small letters or very small bits and bytes, so that by just going to smaller and smaller scales, you could fit more and more information in that region of space that you were handed. So it's already surprising that it's actually finite. But what's even more surprising is that it is not controlled by the volume of the region of space. The maximum amount of information that you can store in this room that I'm sitting in, for example, has nothing to do with the volume of the room, even though that's what you would think. If there's some finite limit to how small you can make things, well, then you divide up the volume into little cubes that are the smallest size you can make anything. Right. And if you have twice as much volume, you can fit twice as many cubes, twice as many bits and bytes, or letters, or whatever you put into those cubes. That's what you would think. So even with a cutoff, even with a finite limitation, you would still expect that the amount of information in nature scales with volume. And of course, that's the interesting part of the story. It doesn't. The thing that ultimately determines how much information I can store in a region of space is the surface area. And that's where the name holographic principle comes from. The holographic principle tells us that the amount of information I can store in this room is controlled by how much area the walls have. I have to measure this area in particular units called Planck units. So think of tiling the wall with little tiny tiles. Each of these tiles is 10 to the minus 33 centimeters on each side. And so put these little tiles all over the walls of the room. And then you get to write a 0 or a 1 onto each of the tiles. So you get 1 bit per tile. And that's how many bits of information you can store.
Yeah, now, so in the tile...
If I do this in this room, that's actually a huge amount of information by ordinary human standards, because the Planck tiles are so tiny. But what's amazing is that it has nothing to do with the volume. It's much less than it would be if I was allowed to put 1 bit per Planck cell, per little Planck cube that I maybe fill up the room with. There are far fewer tiles than there are cubes, and so the upper limit on how much information I can store in this room is really controlled by this much lower number.
Oh, that's interesting. So when we think of the vacuum of space, and string theory suggests that particles are popping into and out of existence in vacuum of space, the information that describes or the amount of information that can appear in any area of space probabilistically is going to be less than what that volume of space would hold.
That's right. Now, I should say that, yeah, the notion of vacuum fluctuations comes out of just quantum mechanics. You don't need string theory for that.
Oh, okay.
And it's true. If you take quantum mechanics seriously, even in empty space, there is an infinite amount of stuff going on. Okay. Because there are these fluctuations happening at smaller and smaller scales. So in a sense, what the holographic principle tells you is that there's not actually a lot of information in those vacuum fluctuations.
Right.
Now, you might say, okay, how do we know that this is, I mean, I just told you that, information goes like the area, great. But,
how do we know?
How do we know? And the real answer to that is because we worked through a lot of examples. Okay, we worked through a lot of examples where we tried to figure out a way to store more information, not necessarily by actually doing it in an experiment, but simply by calculating what would happen if I try to store more information than that in this room. Now, the important thing, and this is why the holographic principle is a statement about quantum gravity. The important thing when you do this thought experiment of trying to break the rule I just gave you and store too much information, the important thing is to keep in mind that that gravity is there. Okay. Now, why is this important? Well, information in a way that is quantitatively, somewhat mysterious, but qualitatively it's not so hard to understand. Storage of information costs energy. So if you, can I have the screen back? Here we go. If you want to store a lot of information, what that means is that you have to put the fields that we have available, such as the electromagnetic field or the fields that atoms are built out of, such as quarks and electrons, you have to put them in an excited state. You have to put energy into them. You can't just let them be alone. You have to make the field have a bump over here to signify perhaps a 1 and no bump over there to signify a 0 and so on. And if you want to cram a lot of information, that means that these bumps are happening on a very small scale. So the field is excited over here and not over there. And I'm trying to cram a lot of information, so I'm giving the field very small scale features. Now, quantum mechanics tells us that you cannot access small scales without paying a certain minimum price in energy. This is why, for example, we are forced to build these gigantic particle accelerators in order to probe, nature on really short distances. We need to smash together particles with enormous energy to make them look at very small distances. So for the same reason, once I try to cram a lot of information into a room, what this means is that I am also cramming a lot of energy into the room. Because I'm exciting fields on short distances in order to actually encode all this information. And this happens no matter how you think about the details of how, whether this is a hard drive or little letters in boxes. At the end of the day, you're going to hit this limitation from quantum mechanics. It's not one that we hit when we write on an ordinary piece of paper, but sooner or later when you try to miniaturize, you're going to hit that particular limitation. And with the information content, the energy of the room is going to go up.
Right.
And now that's the part where quantum mechanics is important. Now, let's think about what gravity does. Okay, gravity is the response of space-time geometry to the presence of mass. Okay. So here there's a couple of steps that maybe I should go through. First of all, I said that storing a lot of information creates a lot of energy. It requires putting a lot of energy into the room. Now, one thing that Einstein taught us 10 years before he discovered general relativity is that energy and mass are the same thing. In particular, if I have a lot of energy, say electromagnetic radiation, that actually gravitates. It has its own gravitational attraction. Okay. The other thing that we learned 10 years later when he discovered general relativity is that if you have an enormous amount of energy, it can gravitate so much that it makes space-time collapse in on itself and form what we call a black hole.
Black hole, right.
And there is a limit. If I specify, the size of the room, there is a limit of how much mass or energy, same thing, I can put into the room before it will definitely collapse into a black hole.
Right.
And once it's a black hole, I can't add more mass or energy to it without it actually becoming bigger. So
bigger and taking up more.
My basic rule was it has to fit in this room. That's the only rule, and I'm not going to violate that one. And
so you're not creating a black hole.
So I don't want to make a black hole.
Right.
I want to ask how much information can I store in the room just before I hit the limit imposed by gravity and the whole thing is going to collapse into a black hole.
Mm-hmm.
And that is where a sort of conspiracy seems to set in. No matter how I try to set up the problem, and no matter how clever, it's like one of these Wile E. Coyote things, you can come up with a new scheme every day of trying to fit a lot of information into the room, and it every time, every time you get frustrated, every time, just when you think, oh, now I'm about to add this last bit of information that is going to make it be more than the area of, and I'm going to violate this holographic bound that I just told you about, you realize, oh my God, the equations of gravity are telling you that actually this thing is collapsing to a black hole. Usually this actually happens quite a bit before you even hit the holographic bound. You don't even come close unless you try to do it in a really smart way. But you can't violate it. Now, why this is true, there's no fundamental reason that we know of in the physics that we currently are aware of that makes it obvious that we can never violate this bound. It's not like, you look at your theory and it's just kind of built into it. It's just that you work through lots and lots and lots of examples, and it's just somehow always true. And it's this really surprising relation between two things that have no right to have anything to do with each other. Again, information, which is basically a statement about quantum mechanics, how many different quantum states you can have in a region, and gravity or the shape of space-time, which is the domain of this classical theory that Einstein invented, general relativity. So we don't understand where it comes from, but we know that it relates to things which we have yet to unify. So there's an obvious guess.
Yes.
Okay? The obvious guess is, well, whatever unifies quantum mechanics and gravity is going to explain this. Once we have that theory, it's going to be completely obvious that this bound on information has to hold. Perhaps because the way that space-time emerges from whatever underlying degrees of freedom there are in that theory is such that there simply aren't more degrees of freedom being used to construct a given space-time region. That there's never more information there to start with. We got ourselves confused when we thought about these fields wiggling here and there in volumes, and then we had to check for every special case. We had to check again that gravity becomes important and prevents us from storing too much information. This should be really obvious, and that's really what the holographic principle is telling us. When you look for the unification of gravity with quantum mechanics, you better look for a theory which is going to make this bound on information obvious.
From people who have written about this in the last couple of years, I've seen work by Eric Verlinde, I think it's Eric Verlinde, who has written about the emergent properties of a holographic universe, and he describes gravity as kind of an emergent force. That it's an entropic force and it's an emergent force, and would that would that make gravity give gravity a different basis in physics than other ideas that suggest that it's based on a particle, like the graviton?
Yeah, no, I think that anyone who takes the holographic principle seriously basically will conclude that gravity in some sense has to be an emergent force. That doesn't mean that everything we know about gravity is wrong. I mean, just like when we, discovered that tables are made of atoms, it doesn't mean that, it hurts in a different way if you bang your head on a table. It's just that you've got a deeper understanding of where it all comes from and how it's all built up. And indeed, I think that Well, the idea that gravity in some sense is not totally fundamental, gravity in the sense of Einstein's theory is not the last word, that's not new. That it might have to, arise in some limit as an effective theory from a deeper, theory that is more precise in situations where Einstein's gravity breaks down, like say near the Big Bang. That is also not terribly new. What the holographic principle is giving us is more specific information about how that kind of emergence has to happen. It has to happen in a very intricate and highly non-trivial way. The way that information has to be distributed in space-time has to respect this extremely surprising bound. And so it really... that kind of information for us is very useful because, after all, this has been a huge task that people have been after for many decades, trying to understand quantum gravity. And so it helps to have some guideposts. It helps to have some constraints to know a little bit better what you should be looking for.
Has anybody been looking experimentally for support or, negation of the holographic principle? Has that been possible yet?
It is a statement about what actually is true in nature. So in some sense, it is a statement that is supported by data. Now, it's one of those statements which is like, the sky is not bright at night. It sounds like a trivial, you don't have to do a big fancy experiment, right? You look out of the window once, you realize the sky is not bright at night. And yet, that one sentence actually contains an enormous amount of very important information about how the universe works. Mm-hmm. That could not be true if the universe was static and filled with stars all the way out to infinity. Mm-hmm. So you just sometimes by figuring out, the deeper meaning of certain observations, you realize that they actually have to tell you something important. So the holographic principle. Well, there would be experimental ways of falsifying it. For example, if you discovered types of matter that effectively are like negative charges for gravity.
Right.
So negative mass matter. Well, that would allow you to balance the attractive force due to all that information that I was trying to store in my room, to sort of balance it out, cancel it out, so that I get to actually cram more and more information into the room. After all, I don't get punished by gravitational collapse because I have some other matter available that I can use to counter the effects of all that information that I've put into the room. So if matter like that was discovered, that would allow us to conclude that the holographic principle is wrong. There are other reasons, not just the holographic principle, why I think it's very unlikely that such matter will ever be discovered.
Right.
But the example illustrates, I think, that the holographic principle is really a statement about nature as we observe it. It's not a statement about it's precisely not a statement about some theory that we happen to love and that we that we are taking all too seriously. On the contrary, it's a statement about something that is actually already happening in nature as we observe it.
Yeah,
and
you observe that there's
a theory that explains it. Except in one case in string theory, but that's a rather limited setting still. Very powerful, very exciting, but it's not yet telling us about the universe that we actually live in, and that is, of course, a limitation.
That is a limitation because not being in our own universe, you can't really test it, or you can describe it maybe, but not test it in any way. Somebody in the chat room was asking if the holographic principle would be consistent with the universe being an image of an underlying object. So is it implicit in the holographic principle that to describe what we know of as a hologram, that it taking information from, say, 2D, 2 dimensions, to 3-dimension representation, would that theoretically make our universe a projection from something else?
Yeah, that's one way that's one way of thinking about it. Exactly. So in fact, my own work has helped clarify, how that projection would work. It's a little bit confusing because in general, you might think, okay, well, if the universe had a boundary, maybe it stops somewhere and there's a sphere and it ends there. Well, then you could imagine that you could project all of the information about what's going on inside the universe onto these little bits, these Planck tiles that sit on that boundary. But realistic cosmology, you usually do not have such a boundary. The universe either keeps going forever spatially, or it might actually be closed, in which case, just like the surface of the Earth. I mean, if you walk around in the Earth, it's not like you suddenly fall off into a void somewhere.
Right.
You just go back to yourself. So where is that information going to live? That's supposed to encode all of the physics going on in the entire universe. And what I realized at some point is that it's very important in formulating what the holographic principle is. Once you want to go beyond the hand-waving statements that I gave you a few minutes ago, it's very important to be precise. And the precise relation between area and information is not one which you could state, like at one instant of time, the information in this room can be described by, bits that fit on the surface of the room at a certain density. The thing that's wrong about that is the one instant of time. The way that the connection actually works is that you need to think about light rays. So light rays have the property that they move pretty fast. I mean, for all intents and purposes, a light ray, of course, crosses this room in an instant. An instant of what a human means by an instant. But to a physicist, they really don't move at fixed time. They move forward at a certain speed, and time also passes as they do so. And the statement of holography, which I call the covariant entropy bound, is really the statement that if you imagine that the walls of the room were flashing up with, I don't know, laser light beams or something that get emanated from them and start propagating into the room, whatever is photographed by these laser light beams, it's the information in those physical systems that can be stored on the walls of the room. Now, if you're talking about an ordinary room like this, that seems like a totally boring academic distinction. I mean, after all, those light rays think of them as X-rays, they permeate everything. They're going to pick up everything that's in the room, the table and me and everything. And so why didn't I just say, well, okay, so everything inside the room can be stored on the walls? Well, I didn't say that because in really exciting physical situations, like when you're deep inside a black hole or when you're looking at the universe on very large scales, it's not always true that light rays that you send towards the center of a room actually see everything that's in that room. Sometimes they end in a big crunch because the world just ends before they had time to get to the middle of the room.
Right.
Or they get terminated by the Big Bang singularity when the universe began. And it's only when you use this formulation of holography that connects areas of surfaces to regions via light rays that emanate from those surfaces. Only then does it really become a completely general and universal statement, and one that really gives us a sort of feeling that nature is conspiring there. It's trying to tell us something. And conversely, once you understand that light rays are basically the connecting piece between the information and the area, it also teaches you where the holographic screens would have to be in completely arbitrary space-times in all the cosmologies that your mind can invent, including the universe that we live in. What you do basically is you think about what we call your past light cone. That's everything in the universe, the whole part of the universe from which signals could have reached us. Okay, so those are regions which are either very old, then they can be far away, or if they're young, then they can't be too far away, because if they're young, that means there hasn't been very much time for light to travel from them to us. And so that's what we usually call the visible universe.
Right.
Now,
everything since light first started traveling after the Big Bang.
Exactly.
So like
that's right.
It's like 700,000 or some odd years after the Big Bang.
13 billion years.
Okay.
It's 13 billion years old, yeah. And so so our past light cone goes out to a distance of billions of light years. And if you follow it back, so if you imagine light rays that are arriving now at our eyes, where did they come from? Well, a second ago they were occupying a sphere of size 1 light second, so that's about the distance to the moon. And then longer ago they were occupying an even larger sphere. And so you can follow this back in your mind, or you can construct a mathematical formula for what the shape of this past light cone is. But as you follow it back in time, it was larger and larger and larger at earlier times because it was coming from bigger distances. But then if you follow it really far back in time towards the Big Bang, at some point, even though it's coming from farther away, the actual circumference of your or area of your past light cone is starting to get smaller again, because inside this past light cone you have a universe which is actually very young and which hasn't expanded very much yet. So as you're going back towards the Big Bang, space itself is contracting so rapidly that this light cone is actually becoming smaller and smaller, and the area is zero. Now, there's somewhere along the way, there's got to be a place where the circumference or area of your past light cone was the largest, because it was zero when it starts right here where I am now, and it's a zero area again when it hits the Big Bang.
The Big Bang, yeah.
So somewhere in the middle, it's maximal, and that's where the holographic screen lives. And you can do that at every instant of time. You can construct your past light cone, and you can store all the information about what's going on in the visible universe on a sphere that is basically the maximal size sphere on your past light cone. So for us, that will be a sphere of area a few billion light years squared. And so that's the sense in which the universe really is a hologram, even though it would be wrong to think of the data as somehow being stored on a boundary where the world ends. It's really, you can think of it as being stored on a sphere that lives somewhere in the middle of the universe.
So somewhere in the middle of the universe lives
I don't mean by that you could go there and look really hard and say, oh, here's zeros and ones. Just thinking about how much information you need to describe everything inside the universe. And that sphere gives you, it gives you that clue. It tells you how much information. Look at my area and divide it by the area of one of these little Planck tiles. So how many Planck tiles fit on me? Well, that's how much information you need to describe everything that happens in the entire observable universe. And that really works.
This topic is so exciting and interesting, and I really see there's just a certain amount of awe in the idea that this could, by explaining things that happen in the observable universe, connect quantum theory, quantum mechanics, quantum gravity, and the larger universe. I mean, there's something so fascinating about being able to do that, and be at the crux of making that happen. What's it like to be working in your field and on this topic right now? What's the physics environment like?
Well, it's a lot of drugs, glamour, money, basically.
Total rock star life, yeah.
Yeah, it can get a little wild. No, it's. I mean, look, it's nice to it's a privilege to work to work on something that you want to do anyway. I mean, this is something that fascinates me, and it's a lot of fun to be thinking about these kind of questions. Yeah. And it's rewarding when you discover something. Now, the hard part is that nature is not, so easy to get, it's not so easy to get the secrets out. It very, very frequently you just go down one road for a really long time, and then after many months or even years of hard work, you realize that it was just the wrong idea. And it's just, it's just not going to work, either because you discover some inconsistency or because you discover a conflict with experiment. And that obviously is, that's the risky part of the business, and it can be disappointing, it can be frustrating. But on the other hand, to actually discover something about how the universe works that maybe nobody knew before, and that's unbelievably exciting, and to even make a small contribution to that kind of progress is rewarding. The other thing that's rewarding is you get to work with extremely interesting people. I mean, I just love talking to my colleagues, to my students, to postdocs. They're all people who care about the same things that I care about, and who are incredibly interesting and smart. And it's a very interactive field. It's very important for us to bounce ideas off of each other, especially in a field like quantum gravity, because quantum gravity sort of marks a point where we know the question is important. We know that the problem is real, but we're not going to get day-to-day input from experiment. The scales at which you would directly probe quantum gravity effects are so dramatically out of the range of current technology, and probably a lot of future technology, that it, any approach to quantum gravity is going to have it's going to have to be based to a large extent on the difficulty of writing down any consistent theory at all. There has to be the criterion of consistency and simplicity. That's going to play a bigger role, not because you shouldn't try to make contact with experiment, but because experiment isn't going to lead you, through every little step.
Right.
It's going to be one of those things where, when Einstein invented general relativity, at first it seemed ridiculous to think that this kind of abstract idea of space bending and so on could possibly, be experimentally tested, let alone have any everyday relevance. But once you understand the theory really well, very quickly you can extract predictions from it, because now you know what kind of questions to ask. Now you know what it might tell you about, and of course the hope is that for quantum gravity that is going to happen as well. But in the meantime, as you try to have ideas about what to do, it's very important to have your colleagues be around and shoot them down for you, and so that's why interaction is so important in our field.
Absolutely, and the experiments that we're looking at right now, 100 years after Einstein brought forward general relativity, we have experimental evidence for it, thanks to satellites and
well, the amazing thing is, once he had the theory,
he could make predictions.
In 1916,
right?
He had immediate experimental confirmation, because he could calculate for the first time some anomaly in how Mercury orbits the sun, called the perihelion precession, and allegedly he had heart palpitations. He got so excited when it came out exactly right. And I can totally understand how you would get nearly a heart attack, because it's just so amazing, to realize that you've glimpsed something that's just true about nature. And but it's just not. It wouldn't be obvious to start with that that's going to be the smoking gun. Once you have the theory, okay, great, you can calculate. Now, with quantum gravity, it's going to be even more difficult, because the road from the level of where the theory is going to be most simply and directly formulated to the energy scales that we can access. There's a lot of trickling down that happens, and there are a lot of complications that can come in when you go from when you try to connect two such different scales. But that doesn't mean that the theory can never make any predictions about what we see. And in particular, it should be able to answer a lot of questions that we may not even have thought of asking.
Yeah, well, the LHC, at this point, based on what you've said, it seems like the LHC is just still this very blunt instrument compared to what we'll need to test quantum gravity. But will the LHC hopefully give us directions for studying and experimenting with quantum gravity?
And again, that would, most likely that would be, hints, not completely conclusive.
Right.
But it could give us some input about quantum gravity. One way in which it might give us input about quantum gravity is if nothing other than the Higgs particle is discovered.
Yeah.
So that would...
or if no Higgs particle is discovered.
Well, if no Higgs particle is discovered, that is somewhat weirder still, and I'd be very surprised if that happens. But if nothing but the Higgs is discovered, then that supports a picture that has come out of string theory and that we've been studying for some time, called the landscape of string theory. It suggests that it basically makes the landscape of string theory become the leading idea for solving what is called the hierarchy problem. And the other ideas for solving the hierarchy problem basically would have to show up at the LHC. Now, if the hierarchy problem is solved in the ordinary way and these particles do show up at the LHC, that doesn't mean that string theory is wrong, because unfortunately we don't understand string theory well enough to predict whether it's going to solve the hierarchy problem this way or that way. But if you don't see any of these conventional ideas, then the landscape of string theory is sort of the only game that remains in town for at least currently, I think, for how the hierarchy problem might be solved. And so that would be indirect evidence, far from conclusive. I mean, these things often get totally overinterpreted, but very intriguing evidence, and that I think would get people more interested perhaps in the landscape of string theory.
When you look at the world, it must be when you look up at the night sky, just to you, it must be a fabulously complex, fascinating thing to look at. And I appreciate the last hour of your time and getting a glimpse into the world that you inhabit. And thank you for sharing the holographic principle with us and for talking a bit about it. An hour obviously was not enough time to delve really deeply into it, but hopefully it gave our audience a bit more understanding of the topic. So Dr. Bousso, thank you very much for joining me today on the Science Hour.
Thank you.
And for anybody who is interested in finding out more about the holographic principle, finding out more about Dr. Raphael Bousso's work, you can visit his webpage at UC Berkeley for more information. And hopefully in the show notes, we will have a link to his lecture, The World is a Hologram, that is also featured at the Lawrence Berkeley National Labs Summer Lecture Series. It's available on YouTube. Everyone else out there, I'm Dr. Kiki. This has been the Science Hour. Next week, we're going to be talking about something sciencey. I haven't scheduled a guest yet, unfortunately, so we're going to be working on that over the next week. But it will be something interesting and fun, I promise you. Until next week, you can follow my pursuits, my sciencey ones, on Twitter or at Facebook, my website, drkiki.tv. Basically, look for me on Google, Dr. Kiki. You'll find me out there. And you can subscribe to Dr. Kiki's Science Hour in iTunes, finding past episodes at twit.tv/Kiki, Kiki. And I will see you next week. That's about it for my Science Hour. Thanks for tuning in. All I ask for is 1 hour a week. And remember that 1 hour a week makes your world a whole lot more interesting. Now for your scientific meditation of the week.